Welcome back to GIS. We'll be looking at application areas. Okay, so GIS are now used extensively in government. GIS is used in military, medical, as well as industry, business, academic, and research. So for a wide range of applications, including environmental resource analysis, land use planning, for wide range, planning, location analysis, tax appraisal, utility, infrastructure, real estate, analysis, marketing, and so on. So one of the first major areas of application was natural resource management, including management of wildlife, habitat, wild and scenic rivers, recreation resources, floodplains, wetlands, agricultural lands, aquifers, forest. Yes. So one of the largest areas of application has been facilities management. So uses for GIS in this area have included locating underground pipes and cables. I'm sure you've seen a number of people trying to dig up here and there, trying to locate cables, pipes, in the water, and so on. Balancing loads in electrical networks, planning facility maintenance, tracking energy use. Okay. Local, state, and federal government have found GIS particularly useful in land management. So GIS has commonly applied in areas like zoning and subdivision planning, land acquisition, environmental impact and policy, water quality management, maintenance of ownership. More recent innovative use of GIS have used information-based on street networks. So GIS has been found to be particularly useful in addressing matching, location analysis, or site selection, development of evacuation plans. We'll look at GIS users. So GIS users, we are specialists. These include programmers, designers, and developers. General users, planners, medics, scientists, administrators, teachers, and viewers. Viewers are simply our clients. Okay, so examples of applied GIS. So urban planning and management. Here we use it for zonings, subdivision, land acquisition, economic development, code enforcement, housing renovation, emergency response, crime analysis, tax assessment. Then in civil engineering, we use it for locating underground facilities, designing alignment for freeways transit, coordination of infrastructure maintenance. In business, we use it for demographic analysis, market penetration, site selection. In environmental sciences, we use it for monitoring environment risk, modeling stormwater runoff, management of watersheds, floodplains, aquifers. Environmental impacts of analysis, as well as toxic facility siting, groundwater modeling, and contamination tracking. In education, in administration, we use it for attendance of area maintenance, enrollment projection, school bus routine. In real estate, we use GIS for neighborhood and land prices, traffic impact analysis, determination of highest and best use. In healthcare, we use it for epidemiology, need analysis, service inventory. In political science, we use it for the districting analysis of election results, and also predictive modeling. So basically, that's how we use it. I'm not going to look at GIS data types and models. Spatial data are computer representation of our spatial features of the real world, representation of the real world. A modeling language for GIS is for GIS database is a spatial data model. So a spatial database holds a digital representation of the real world. Among spatial data models, we can distinguish two major types: field and object-based models. So field-based models consider spatial phenomena to be of a continuous nature, where in every point in a space, a value of the field can be determined. Examples of such phenomena are temperature, barometric pressure, or elevation. Object based models consider a space to populate by well-known discrete bound. Okay, examples include parcels, building, and others. It is therefore common to see geographical phenomena of spatial features in terms of field, objects, boundary simply defining extent of interest. Okay, the primitives that are used to represent features in the object view comprise point, line, polygons, volume. It is called vector-based approach. In the field view of this part, to use divided up completely into regular squares, triangles, or cubes that define two or other dimensional rasters. So the more common name for the field view approach is the raster-based approach. GIS data types. A GIS deals with spatial data, e.g. parcels, rivers. Okay. Their attributes and characteristics, that is location, length, so on, and the relationship between the objects, e.g. parcels, boundaries. The objects are stored in the database with geometric primitives, that is volumes, lines, and the relationship between them, that is now the topology. Spatial data have the following characteristics: spatial reference, that is where, attributes, what, then spatial relationships, technology or use in what relationship, then temporal component, different component, that is when. Okay, so the source is Canis 2004. It is common to equate GIS data with three triptychs characteristics: description, referencing, time. So description is the attribute, reference is the spatial reference data, and time as a reference, and description may change over time. The basic data type in GIS reflect traditional data found on a map and currently digitally in a GIS or spatial database. So accordingly, GIS technologies utilize two basic types of data. These are spatial data, that is location, geometric, attribute data, and also spatial relationship. So spatial data describe the absolute and relative location of geographic features. Then attribute data describe the characteristics of the features. So these characteristics can be quantitative or qualitative in nature. Attribute data is often referred to as tabular data. The coordinate location of forest would be spatial, while the characteristics of the forest stand, e.g. the cover, dominant, crown, it would be attribute. relationships, or which are rules of behavior. Topology such as coincidence, adjacency, and conjectives. Spatial data models. Traditionally, spatial data has been stored and presented in the form of a map. Three basic types of spatial data have evolved for storing geographic information data. These are vector, raster, and image. So a raster is represented like this, then vector like this, then we have the real world. So vector models use discrete points, lines, areas corresponding to discrete objects within the name or code of number of attributes. Raster. Okay, so you can see vector there. Then raster. Raster models use regular space grid cells in specific sequence. An element of the grid cells is called pixel, which contains single attributes. Image data. Utilizes techniques very similar to raster data, however, typically lacks the internal formats required for analysis and modeling of data. So images reflect pictures or photographs of the landscape. The data models represent a set of guidelines to convey the real world code entity to the digitally and logically represented spatial objects consisting of the attributes and geometrics. GIS data presentation. So spatial data in GIS represents features that have a known location on Earth, points, X and Y location, polygons, connected Y and Y locations making a closed figure. Then lines, we're talking of connected Y and X locations without closing. Then raster, we're talking about row and column matrix represented in the geographic space. Vector in the data structure. The method of representing geographical features by the geographical elements, points, lines, and polygons is called the vector method or vector data model. Vector data represent geographical space that is intuitive and reminds of analog. So vector data mostly incorporates the use of a topological structure, especially the arc, node, and structure explained below. Raster data structure. Raster data models incorporate the use of a grid cells structure where the geographical area is divided into cells identified by rows and columns. So a raster is a tessellation of the surface. What is raster data? So a raster-based system stores data by using grid of cells, unique reference coordination. Coordinates represent each pixel either at corner or in the middle of a cell. So each cell or pixel has the discrete attributes assigned to it. Raster data resolution is dependent on the pixel or grid size, may vary from sub-meter to many kilometers. So raster data stores different information in layers, elevation, soil types, geology, forestry, and etc. Generally, raster data requires less processing than vector but consumes more computer storage. For example, remote sensors or satellite stores data in raster format. DTM, which is a digital terrain method, and digital elevation models. Then you have continuous data, which is field sort data. A raster data or a raster can use reasonable geometric shape as long as it can be connected in such a way to create continuous surface. Okay, so this is what I have been talking about in my explanations. Okay, you can look at them. So this is how we compare raster and vector data models. Raster models, it is simple. It is a simple data structure. Where vector, it provides more compact in structure than raster. Okay. Okay, maybe let's look at the advantages of raster models first. So overlay operations are easily and efficiently implemented in raster. Then again, raster has an advantage of highly spatial visibility, variability in efficiency represented in raster format. Then raster data format is more or less required for efficient manipulation and enhancement of digital images. Okay. On the other hand, we have the vector advantages. The first one, I'd say it provides a more compact data structure than the raster model. It provides efficient encoding of topology as a result, more efficient implementation of operations that require topology, such as network analysis. The vector model is better suited to be supporting graphics than closely approximate hands-on map. Okay, allow me to end here for now, as I'll continue next time on attribute data and also attribute data model. This has been Preston Winga. Till next time. Thank you.